On this slide, we're going to begin talking about acids. Acids produce hydrogen ions, which have a +1 charge. And they produce hydrogen ions when they're in solutions. Acids are all around us. We can find acids in windshield wiper fluid, in cleaning products, in foods like salad dressings, fruit, yogurt. There's even acid in our stomach, which helps digest our food. And acids are associated with sour taste in foods, which is why I've shown a photo of a lemon here. There is what gives the lemon its tartness is acid, and that is the case for apples as well. Okay, let's go on to our next slide and learn about binary acids. Binary acids are when we have a hydrogen plus a nonmetal. And binary means two elements, so it's just these two elements, the hydrogen and a nonmetal. We name these acids by using the prefix hydro and then the root name of the nonmetal element, and then adding the ending ic, I-C, and then after that the word acid. All right, so let's take a look at our first couple of examples. So here we have hydrogen and chlorine. So following the naming, we call this hydrochloric acid. So take a look at the next one. Hydrosulfuric acid. All right, so see if you can predict what we'll call the next three. Okay, so the next one is hydrobromic acid. For the following one, we have hydrogen and iodine, so we have hydroiodic acid. And for the next one, we have hydrogen and fluorine, so it's hydrofluoric acid. All right, so now we've learned how to name binary acids and how to identify a binary acid. You may have already been familiar with hydrochloric acid. That's the type of acid that is used in some cleaning solutions. Okay, let's move on to our next slide about oxoacids. So when we talk about oxoacids, it's helpful to know the basic formula for them. Oxoacids typically contain one or more hydrogens, a nonmetal, and one or more oxygens. Typically, we can look at the formula and see that it's composed of one or more hydrogens and a polyatomic ion. So the nonmetal and the oxygens are often a polyatomic ion we can recognize. Now the number of hydrogens in the formula is generally equal to the charge on the polyatomic ion. So if we had, for instance, our first acid shown here is sulfuric acid. That is from the sulfate ion, which has a charge of -2, and we do see that sulfuric acid has 2 hydrogens. If we look at nitric acid, the next one down, we see the ion that's associated with that is nitrate, which has a charge of -1, and we see that nitric acid does indeed have 1 hydrogen. And this pattern holds true for phosphoric acid, which stems from the phosphate ion, and which has a -3 charge, and sure enough, phosphoric acid has 3 hydrogens. So we can see the pattern for oxoacids. Okay, now let's take a look at how we name these acids on the next slide. So here we see the pattern to naming oxoacids, and the pattern depends on the ending of the polyatomic ion on which the acid is based. Now remember, we said that there are as many hydrogens added to the acid as there are negative charges on the polyatomic ion. So that helps us determine the formula and then the name. So you can see here where we have given an example with chlorate ion. And so chlorate ion has a -1 charge, so we would add 1 hydrogen to the beginning of that formula to get HClO3. And because it's an 8 ion, we then change the ending to ic and add the word acid. For chlorite and ite ions, We follow the same pattern of adding a hydrogen for each negative charge. So we see here HClO2 is the formula of the acid, and anions with the "ite" ending give us an acid name with an OUS ending, us acid. So this becomes chlorous acid. See if you can determine the formula for nitric acid and nitrous acid when you're provided with the two polyatomic ions that go with them. Once you've tried to do that, you can go ahead and click to the next page and see if you were correct. Here we continue naming oxoacids, and you can see if you got the correct formula for nitric acid. We started with the nitrate ion, NO3 with a -1 charge, which means we add one hydrogen to the beginning of that formula to get HNO3. Because we started with an 8 ending, our acid is named nitric acid. In the next row, we had nitrite ion, and that also has a -1 charge, so we added one hydrogen to it to the beginning of the formula to get HNO2. And because we had an "ite" ending on our ion, we call this nitrous acid. Okay, so that is how we name and predict the formula of oxoacids. So we can predict the formula from an oxoacid knowing its polyatomic ion, or if we know how to name these. Okay, let's take a look at our next slide. All right, so on this slide, we're going to practice determining the ion that the acid comes from, and once we do that, we're going to try naming the acid. So we could look at the first one and we could see that sulfate ion is within this formula, and we know that sulfate ion has a 2- charge. So we can identify the ion, and we know the ion ends in ATE, 8. So the name would be sulfuric acid. Now you try the next one. Okay, and go ahead and try the third one, and then when you're ready, let's go to the next slide and talk through these. All right, so let's take a look at our first one. It was H2SO4, and we can see the sulfate ion in there, and the sulfate ion is SO4 with a 2- charge. We know it's called sulfate ion, so that means the name of the acid will be sulfuric acid. For the next one down, we see H2SO3. We recognize SO3 is the formula of the sulfite ion, which has a 2- charge. The "ite" ending means we change the suffix to us, so we get sulfurous acid. For the next one down, we have H2CO3. We recognize CO3 as the polyatomic ion carbonate, which has a 2- charge. So we change the ending from 8 to ic and add the word acid to get carbonic acid. Okay, so that is how we name oxoacids, or how we can use the same information to go from a name to the formula. All right, let's go ahead and take a look at our next slide. Okay, so you've got some practice now on naming oxoacids. I'd like you to try naming these 5 yourself. Make sure you pay attention to the ending of the name of each of these. Okay, and when you can pause this while you do that, and when you're done, go ahead and restart the recording and we can talk about the answers. Okay, so let's take a look at our first one. If we started with nitrate ion, we would then go convert that to nitric acid. As we started with 8, 8 goes to ic. 8, I ate something icky. So 8 to ic gives us nitric acid. The next one is nitrite. Ite goes to an us ending, giving us nitrous acid. Our next one is chlorate. ic to ate gives us chloric acid. Chlorite, ite goes to us, gives us chlorous acid. And phosphate, we go from it to ake, so we go from ate to ic. So ate becomes phosphoric acid. Okay, how did you do with those? All right. All right, well, that concludes our time discussing learning about acids, and we're now going to review a number of Unit 5 topics. This is a really important unit in Chem 101, and we cover some really important material, such as calculating formula masses and molar masses, and determining the number of moles from formula units, and determining the number of formula units from moles. So we're going to do an example of each of those, and we'll do examples of formula mass and molar mass and molecular mass. We'll also review naming ionic compounds and writing ionic compounds from names, and we'll practice binary molecular compounds, both writing from names and going back and forth. Okay, all right, so let's commence. So previously in this unit, we learned how to use formula mass and to do formula mass and mole calculations. So here we're given 1.73 times 10 to the 21 formula units of magnesium sulfate, and we want to know how many moles that is. So first, we make sure we know what our given is, 1.73 times 10 to the 21st, and we want moles. So we're going to set this up the same way we've been setting up problems before. We put our given over to the left, taking note of the units in the given. And the units in the given will be in the bottom of our conversion factor. So on the bottom of our conversion factor, we'll need to know how many formula units are in a mole. So there are 6.02 times 10 to the 23rd formula units in a mole. So we have 6.02 times 10 to the 23rd formula units on the bottom, and we have 1 mole on top. And we then do the math. 1.73 times 10 to the 21st divided by 6.02 divided by 10 to the 23rd gives us 2.87 times 10 to the negative 3 moles. Now your calculator may have provided a decimal, and that's okay, but you should also know how to convert that to scientific notation. Okay, so we remember that we know there are 6.02 times 10 to the 23rd formula units in a mole, and that's going to be an important thing to remember. And what is the name of 6.02 times 10 to the 23rd? That number has a name. Do you remember that that's called Avogadro's number? Okay, let's take a look at our next problem. All right, so here we have a problem with 4.5 moles of calcium chloride is needed by a student, and we want to know how many formula units are in 4.5 moles. So we know our given is 4.5 moles and that our wanted is formula units. So here, once again, we need to know how many formula units are in a mole. And we know that that's Avogadro's number, 6.02 times 10 to the 23rd formula units in a mole. Now you can go ahead and pause this recording while you set up this problem, and then we'll talk about it. Okay. So our given was 4.5 moles, so we put that over to the left, and then we use our conversion factor. Now, since our given unit was moles, we know that moles will go on the bottom of our conversion factor, and formula units will go on the top. So I have 6.02 times 10 to the 23rd formula units on top. So now I do the math. 4.5 moles divided by 1 mole times 6.02 times 10 to the 23rd gives us 2.7 times 10 to the 24th formula units of calcium chloride. Okay, I hope that went pretty well. Let's take a look at our next problem. Now we're going to take a look at practicing calculating formula mass. So remember that formula mass is expressed in units of AMUs, and we look at the formula mass, the average atomic mass on the periodic table, and we add that up for each element in a compound. Now, if the element is present in more than one atom, we have to multiply the atomic mass by the number of atoms of that element in the compound. So if we look at calcium sulfate, we would have the atomic mass of calcium plus the atomic mass of sulfur plus 4 times the atomic mass of oxygen. Okay, so I'd like you to do the formula mass for these, and then you can click to the next slide to check your work, and we'll go over them together. So here we have the formula mass calculated for calcium sulfate. Now, I used a periodic table that has 4 significant figures. If you used a different periodic table, you may have very similar numbers that are slightly different, and that may affect the number of sig figs you have. So calcium has an atomic mass of 40.08, and we have that once, plus the atomic mass of sulfur, 32.07, and there are 4 oxygens, so we have the atomic mass of oxygen, 16.00, 4 times. When we add this up, this gives us 136.15 AMU as the formula mass for calcium sulfate. Next, we look at the formula mass for ammonium phosphate. So we have 3 ammonium ions. So we have 3 nitrogens, 4 hydrogens, 1 phosphorus, and 4 oxygens. So we need to take into account that we need to multiply the atomic mass of nitrogen by 3, the atomic mass of hydrogen by 3 times 4, which is 12, and then we have 1 phosphorus, and we have 4 oxygens, so 4 times the atomic mass of oxygen of 16. When we do all this multiplication and add this up, we get a formula mass for ammonium phosphate of 149.10 AMU. Next, we look at aluminum phosphide. We have 3 aluminums at 26.98 AMUs each, plus 1 phosphorus at 30.97 AMU, for a total formula mass of 111.91 AMU for aluminum phosphide. Okay, let's take a look at our next slide. On this slide, we are asked to calculate the molecular mass of these 2 molecular compounds. Remember that molecular mass is a subset of formula mass, so it's going to be calculated exactly the same way. So I'd like you to take a look and calculate the molecular mass of these 2 compounds, and when you're done, you can go ahead and click on the next slide and we'll go over them together. Okay, how did that go? So let's talk about our first compound. So we have 2 hydrogens and 1 sulfur in this compound. So we have 2 times 1.008, the atomic mass of hydrogen, plus 32.07, the atomic mass of sulfur. This gives us a molecular mass of 34.09 AMU. Next, we look at tetrasulfur tetranitride. There are 4 sulfurs and 4 nitrogens, so each atomic mass needs to be multiplied by 4. So 4 times 32.07 for the sulfur, plus 4 times 14.01 for the nitrogen. And this gives us a total atomic mass of 184.3 AMU. You may wonder why there's only 1 decimal point after the decimal. But you'll notice that we multiplied 32.07 by 4, and that gave us a 4-digit number with only 1 number past the decimal, 1/10. And that meant that we couldn't carry down the hundredths from these numbers, so that limited us to a decimal, to 1 decimal place, or to 4 sig figs, which gave us 1 decimal place. Okay, all right, so let's go ahead and take a look at our next slide on molar mass. So here we're being asked to calculate molar mass. Now remember, a mole is a really big group size, but molar mass is just like formula mass. It's calculated exactly the same way. The only thing that's going to be different are the units. Formula mass is expressed in AMUs, and molar mass is expressed in grams. So we're going to calculate this exactly the same way that we calculated formula mass or molecular mass, but this is going to be expressed in units of grams. Okay, so I'd like you to go ahead and work on these 3 and calculate the molar mass for each of these compounds, and then we can walk through it together on the next slide. So here we are calculating the molar mass of calcium sulfate. Calcium at 40.08 grams per mole plus sulfur at 32.07 grams plus 4 times the molar mass of oxygen, which is 16.00, gives us 136.15 grams of calcium phosphate per mole. Now, if you look at the formula mass that we calculated for the same compound, you'll see we calculated the same number. The only difference is in the units. Now let's take a look at our next compound here. Sulfur hexafluoride. We have one sulfur at 32.07 grams per each mole and 6 fluorides. So fluorine has an atomic mass of 19. We have 6 of them, so 6 times 19. And this gives us a total molar mass of 146.1 grams. Now, our next compound is nitric acid, and we have 1 hydrogen and 1 nitrogen and 3 oxygens. So we have the molar mass of hydrogen, 1.008 grams, plus the molar mass of nitrogen, 14.01 grams, plus 3 times the molar mass of oxygen, 3 times 16.00. This gives us a molar mass for nitric acid of 63.02 grams. Okay, if you have questions about this, please go ahead and email me about formula mass, molecular mass, or molar mass. All right, now we're going to move on to talking about ionic compounds. So this is review about naming ionic compounds. We recall that the cation will be named first and is also first in compound formulas. The anion is second in both the name and in ionic compound formulas. The anion has its ending changed to IDE, such as in sodium chloride. Now, when a cation can have multiple oxidation states, we have to specify in the name which cation we are using. So for example, iron can have multiple oxidation states. So when we name this compound that has both an iron and a sulfur in it, we would call it iron 2 sulfide to specify that the cation here has a charge of +2. We only do this when the cation can have multiple oxidation states. So you would need to look on your polyatomic ion sheet and memorize those elements that can have multiple oxidation states. They're listed, things like iron, tin, lead, copper, cobalt, mercury. Now, how do we figure out which cation we have? Let's take a look at our next slide and do that. So some transition metals can produce cations with multiple oxidation states, and we just talked about some examples. Iron was one, cobalt was one, copper was one. And this can be true also of a couple metals that aren't transition metals, and that is lead and tin. So what do we do when we have a formula with one of those cations and we need to figure out which charge it is before we can name it? Well, we use the anion because we will know the charge of the anion. So if we were to take a look at that iron and sulfur compound, we know what the charge on a sulfide anion is. We know it's 2-. And we know that iron can have a charge of +2 or +3. And we see that in the formula, we have 1 iron plus the sulfide with a -2 charge that gives us a charged balanced compound with a charge of 0. So would it be +2 or would it be +3 that we could add to -2 that would give us 0? What plus -2 equals 0? And that would be +2. So that tells us that we have the iron 2 ion here, and we would name this iron 2 sulfide. Okay, let's take a look at doing this a couple of more times so you get a better idea of exactly how to do this. So here we're given a compound that has cobalt and chlorine. So we want to use the anion to determine if we have cobalt +2 or cobalt +3. We have 2 chloride ions. We know that chlorine is a group 7 element, and that group 7 elements form anions with a -1 charge. Now we have 2 chlorines, so we have a -2 charge from the chlorine. and we have 1 cobalt. So what plus -2 will give us a total charge of 0? So that would be +2. So here we have cobalt 2. So we name this compound cobalt 2 chloride. Now let's go on to our next compound. Here we have a compound with copper and sulfate ion. Now we know the charge of the polyatomic sulfate ion. We know it's 2-. So we have 2- plus something equals 0. But there are 2 coppers here, so when we say it's -2 plus 2 somethings equals 0. So -2 plus 2 somethings equals 0, that must be a negative. That must be a +1. So -2 plus 2 times +1 equals 0. So this is copper 1 ion. So we would call this compound copper 1 sulfate. Okay, so let's take on the next slide. So here I'd like you to practice finding the oxidation state of the cation in these 4 compounds. Each of these cations can have multiple oxidation states, and this type of practice is important to get good at doing this. Remember, you're going to use the charge on the anion, and you have to consider how many of that anion you have as well. Okay, so I'd like you to go ahead and work through that, and when you've finished, you can click to the next slide and we'll go through each one. So here we work through finding the cation oxidation state in the compound that contains cobalt and phosphorus. So cobalt can have a +2 or a +3 charge. Now we know the charge on the phosphide ion because we know phosphide is a group 5 element, and the group 5 elements, when they form anions, have a -3 charge. So phosphide has a -3 charge. So -3 plus 1 of something equals 0. That something must be +3. So this will be cobalt 3 phosphide. Let's take a look at the next one. Here we have tin and chlorine. Chlorine is a group 7 element, and group 7 elements form ions with a -1 charge, and we have 2 of them here. So whatever state tin is in plus -2 equals 0. So -2 plus what equals 0? That would be +2. So here we have tin 2 chloride. All right, let's take a look at the next one. All right, here we have lead combined with 2 oxygens. Now we know that the charge on an oxygen anion, it's from group 6. We know that the group 6 anions have a -2 charge. That's for 1 oxygen, but we have 2 oxygens. So we have 2 times -2. So we have a -4 charge from our oxygens. So -4 plus the lead equals 0. So lead must be +4. So this would be called lead 4 chloride. Now let's take a look at our next compound. Here we have copper with 2 hydroxide ions. Each hydroxide ion has a -1 charge. We know this from memorizing our polyatomic ion sheet. So I have 2 times the -1 charge plus copper equals 0. So -2 plus copper equals 0. So copper must equal +2. So this would be copper 2 hydroxide. Okay, if you have questions about this, be sure you email me, and there are places you can practice this in the Unit 5 worksheet. Okay, let's go on to our next slide. Here we want to practice writing ionic compound formulas. So here we're going from the name to the formula. All right, so remember that the cation comes first always, and the anion has its ending changed to IDE unless it's a polyatomic ion, and then you just put the name. Okay, so you can go ahead and work on these 7 compounds and name them, and then we'll go over them. I'm sorry, you're going to write the compound formulas, not the compound names. Yes. So you'll go ahead and write the formula for each of these compounds, and then we'll work through them together. All right, so we started with the name sodium chloride, the symbol for sodium, Na of course, and chloride ion is Cl. You notice that we don't put the ion charges in the compound formula. We can put them on the separate ions, but when we write the compound formula, we don't write the charges. Next, we have potassium sulfate. The symbol for potassium is K. Now, how did we know there were two potassiums? It doesn't tell us in the compound name for ionic compounds. Well, we have to know the charge on the sulfate ion. The polyatomic ion sulfate has a charge of -2. Therefore, for this compound to be charge balanced with the potassium, which is from group 1, potassium, when it forms an ion, has a +1 charge. So to balance out the -2 of the sulfate, I needed 2 potassiums with a +1 charge. So I have +2 from the 2 potassiums and a -2 from the sulfate to give me a total 0 charge on this compound. Next, we have aluminum nitrate. So aluminum has a +3 charge, and we know this because aluminum is in group 3A, and the elements that form ions in that group form ions with a +3 charge. So we have 1 aluminum, and nitrate has a -1 charge. So we are going to need 3 nitrates. So 3 times -1 to give us -3 to balance out the +3 from the aluminum. Okay, let's take a look at our next one. Here we have lead 2 sulfate. Oh, so they're telling us that the lead ion has a +2 charge, and we know that the sulfate has a -2 charge, so we just need one of each. Next, we look at the compound called sodium sulfate. Now, sodium has a +1 charge, being in from group 1. So when the group 1 elements form ions, they each have a +1 charge. Sulfate has a -2 charge. How can we balance out the -2 from the sulfate with our +1 from sodium? We use 2 sodiums, so we have 2 times +1 to give us +2 to balance out the -2 from the sulfate. Next, we have ammonium phosphate. The ammonium ion has a formula of NH4 with a +1 charge. The phosphate ion has a -3 charge. How do we know the charges on either of these? From memorizing them from the polyatomic ion sheet. So we have a 3- from the phosphate and a +1 from the nitrogen, or from the ammonium ion. So we're going to need 3 ammonium ions. 3 times +1 gives us +3 to balance out the -3 from the phosphate. So when we add -3 and +3, we have a total of 0, because we always want a 0 charge on ionic compounds. Next, we look at copper 1 sulfide. So here we have copper 1. So each copper ion has a +1 charge. The sulfide ion, being a group 6 ion, has a -2 charge. So to get +2 to balance out the -2, we're going to need 2 copper ions. So 2 times +1 is +2, and that balances out the sulfide's -2 for a total charge of 0 on this ionic compound. Okay, as always, if you have questions about this, please email me. And now we're ready to practice writing the formulas of binary molecular compounds on our next slide. Here we're practicing writing binary molecular compounds. And you'll notice that in the binary names, remember, we use the Greek prefixes. So you need to know what each Greek prefix means to know how many of each element to put in the formula. Now, the first name in the formula is the first name in the Let's try this again. The first element in the name is the first element in the formula, and the second element in the name is the second element in the formula. Okay, so I'd like you to go ahead and practice naming these writing the formula for these 7 compounds, and we'll go over them together on the next slide. All right, so sulfur hexafluoride. So we have S for sulfur, and hexa is 6, so we have 6 fluorines in this, so SF6. Our next compound is carbon monoxide. Now remember, when we have one of the first element, we don't use the mono, and we have 1 carbon here, but we don't use the mono for the first element. But we do for the second element, and we have 1 oxygen here, so we do use the mono, so this is carbon monoxide. Our next compound is phosphorus pentachloride. So we have in the formula P for phosphorus, and penta is 5, so we have 5 chlorines in our formula for phosphorus pentachloride. Our next compound is tetraphosphorus decoxide. Tetra is 4, so we're going to have 4 phosphorus in this formula, and dec is for 10, so we're going to have, or deca is for 10, but we remember when we have the A and the O next to each other, we drop the A, so we have 10 oxygens in decoxide. Our next compound, nitrogen dioxide. Now remember, again, when we have one of the first element, which in this case is nitrogen, we don't use mono on the first element. So we just call this nitrogen, and then we name it for the 2 oxygens dioxide, so nitrogen dioxide. Next we have diphosphorus pentoxide. So di for 2, so 2 phosphorus, and pentaoxide becomes pentoxide when we drop the A, because we don't have the A and the O together, and penta is 5, so we have 5 oxygens. Next we have dihydrogen monoxide. So dihydrogen, so that's 2 hydrogens, and monoxide, so mono for 1 oxygen, and that gives us H2O. Yes, there's a much more common name for that. That's water, of course, but I do want you to be able to name that compound using the binary molecular compound naming system. Okay, so now we're going to move on to naming compounds where we're going to have ionic and binary molecular compounds mixed together on our next slide. On this slide, I'd like to practice our skills on determining which compounds are binary molecular compounds and which are ionic compounds. Now remember, a binary molecular compound can be composed of 2 nonmetals or a nonmetal and a metalloid. And binary means 2. So if you see more than 2 elements, that's a good tip-off that it is not a molecular compound, but is an ionic compound. Okay, so I'd like you to go ahead and circle the ionic compounds, or write down which ones you think are the ionic compounds. And you can pause this while you do that. Okay, and now if you click, you'll see that I've circled the ionic compounds. So potassium sulfide, that's a metal and a nonmetal, so that's an ionic compound. Our next compound was sulfur trioxide, which is 2 nonmetals, so that meets the qualification for a binary molecular compound. Next we have ammonium nitrate with an ammonium ion and a nitrate ion, so clearly that's going to be an ionic compound. Then we have sodium bromide. Sodium is a metal and bromine is a nonmetal, so this is an ionic compound. The next one, we see there is a sulfate ion in it, so this lead 2 sulfate is an ionic compound. Next we have carbon monoxide. Carbon is a nonmetal, oxygen is a nonmetal, so this is a binary molecular compound. And then we have cobalt in our next compound combined with chlorine. Cobalt is a metal and chlorine is a nonmetal, so this is also an ionic compound. All right, now why is it important for us to be able to determine which are ionic and which are binary molecular compounds? Because we need to distinguish naming. So the the binary molecular compounds are named with using Greek prefixes, but ionic compounds are not. And in addition to naming binary molecular compounds and ionic compounds, we've also learned how to name acids. So we need to be able to distinguish an acid. And an acid usually has a hydrogen as the very first thing in the formula. So watch for that for acids. Okay, let's go ahead to our next slide on naming compounds of any particular variety. So here we're asking you to name these compounds. So you could be naming an acid, or a binary molecular compound, or an ionic compound. So you'll need to be able to distinguish the difference to be able to know how to name each of these compounds. So this connects all the information, some of the information that we've learned about naming in Unit 5. So I'd like you to go ahead and do that for these 8 compounds, and then we will walk through naming any that you had difficulty with on the next slide. Okay, here on this slide we have our first compound is hydrobromic acid. So we discussed this earlier in today's lecture, how to name these binary acids that have just 2 elements in them. Next we have xenon tetrafluoride. Now xenon tetrafluoride is composed of 2 nonmetals, so this is a molecular compound. So we use the binary molecular naming system, and this becomes xenon tetrafluoride. Next we have a potassium and an iodine. This is a metal and a nonmetal, so this is an ionic compound, so we use the ionic compound naming system, and this is potassium iodide. Next, we recognize that this is a polyatomic ion with 2 hydrogens on it, so this is an acid, and this compound, the polyatomic ion, is sulfate, and remember 8 gives us ic, so sulfate becomes sulfuric acid. Next we have a compound with a metal in it and a polyatomic ion, so this must be an ionic compound. So we name this sodium nitrate. Below that we have a metal and a polyatomic ion again, so this is another ionic compound. Now iron can have multiple oxidation states, so we have to look at the charge on the sulfate ion, which is -2, and we have 1 iron balancing it out. So -2 plus 1 iron equals 0. Therefore, the iron must be +2. So we name this iron 2 sulfate. Looking at our second to last compound, we have cobalt with a hydroxide ion. So this must again be an ionic compound. Now, cobalt again has multiple oxidation states, so we use our knowledge of the polyatomic ion hydroxide. It has a -1 charge, and there's 3 of them. So we have a -3 charge, so -3 plus cobalt equals 0. Therefore, cobalt must be +3. So this is called cobalt 3 hydroxide. Next we have an ammonium ion and a carbonate ion. This is an ionic compound. So we name this according to the ionic compound names, and we name this for the polyatomic ions that are in it. So this is ammonium carbonate. Okay, so this gave us some practice naming. So let's go ahead, and now I'd like to go take a look at our next slide. On this slide, we've given you a list of ions, and we would like you to write the formula of the acid associated with that polyatomic ion. So to do this, you need to remember the correspondence between hydrogens and charges on the ions. Okay, so I'll give you a moment to do this, and when you've done that, you can click forward to the next slide and we'll talk through these. Here we have the original list of ions, and on the right we have the acid that is formed by that ion. So the nitrate ion gives us nitric acid with one hydrogen. Because the nitrate ion has a -1 charge, we add one hydrogen to get nitric acid. So remember that the charge on the polyatomic ion tells us how many hydrogens we add to the polyatomic ion to get the acid. So the sulfate ion had a negative charge of 2, so we added 2 hydrogen ions to make sulfuric acid. Carbonate had a negative charge of 2, so we added 2 hydrogens to get carbonic acid. Phosphate ion had a -3 charge, so we added 3 hydrogen ions to get phosphoric acid. Nitrite had a -1 charge, so we added 1 hydrogen to get nitrous acid. And chlorate ion had a -1 charge, so we added 1 hydrogen to get chloric acid. Okay, so that was a little bit of review on naming the acids that we learned a little while earlier today. So we're going to go on to our next slide where we're going to be practicing writing formulas for compounds. All right, we have a little bit more naming practice here, and this naming is using transition elements. So each of these compounds contains an element from the transition metals. So I'd like you to go ahead and write the formula that goes with the following names for each of these 7 names. And we will walk through them on the next slide. All right, so silver has a +1 ion, and so we need 1 silver, and chloride forms a -1 ion, being a group 7 element. So we have 1 silver and 1 chlorine in silver chloride. Nickel bromide. So nickel has a +2, forms a +2 ion, and bromine forms a -1 ion. So we have to have 2 bromines, 2 times -1 from bromine to balance out the +2 of the nickel charge. Now, how did we know the charges on silver and nickel since we can't really tell from what group they're in the transition elements? We had to memorize them from the polyatomic ion sheet. Next, we have cobalt 2 sulfide. So this tells us cobalt will have a +2 charge, and it's combined with sulfur, which forms a -2 ion, as group 6 elements do. And so we have 1 cobalt at +2 and 1 sulfur at -2 for cobalt 2 sulfide. Next, we have zinc sulfate. We learned on our polyatomic ion sheet that zinc has a +2 charge on its ion, and we know that the sulfate ion has a -2 charge. So we need 1 of each, 1 zinc and 1 sulfate in this formula. Tin 4 carbonate tells us that the charge on the tin ion is +4. We know from our polyatomic ion sheet that the carbonate ion has a -2 charge per ion, but we need to balance a +4 charge. So we're going to need 2 of those -2 charges to get a -4. So we have 1 tin at +4 and 2 carbonates at -2 times 2 to give us a -4 charge, so that we have an overall charge of 0 on tin 4 carbonate. Next, we have copper 1 phosphide. Now we have +1 on the copper and -3 on the phosphorus. So to balance the -3, we're going to need 3 times +1 for the copper. So we have 3 coppers and 1 phosphorus in our copper 1 phosphide formula. And these are, of course, all ionic compounds, which is why we are naming them this way. Then we have iron 3 phosphate. This tells us that our iron has a +3 charge. So we have a +3 charge on our iron, and phosphate ion has a -3 charge. So we have 1 iron and 1 phosphate on here. Okay, I would also remind you to review what to do when you have, we covered that already, so just never mind that. We already covered that, so that's good. Okay, all right, if you have any questions about any of the material covered in this lecture, please go ahead and email me at hdodson@wccnet.edu. Okay, great. I hope you enjoyed this material and are getting well prepared for Test 5, which begins on Friday, October 16th. Okay, thanks.